Good morning, everyone. I'm Xiang from Huazhong University of Science and Technology, China. So it's my pleasure to do a continuous talk. I mean, last year I was here and do a presentation, and this year I'm also very excited to do a presentation here. So in the outline, I would like to present some background and motivation and make a very brief recap of my research activities at NAB, and especially the progress during 1 year. Okay, and finally, I will present something about the underwater optic cable tracking and underwater intervention. So this is outline, and firstly, the background and motivation. So a few years ago, the National Library of Marine Science and Technology in China launched a very interesting ocean initiative. So it's a transparent ocean initiative. So in this case, we would like to use ocean satellites to do the remote sensing of the ocean. And secondly, we would like to use some buoys and ships or autonomous surface vehicle or cargo buoys or something else to do the air-sea interface. And also, we would like to have some deep sea stars by using the submerged buoys and some moving underwater vehicles. And finally, we also would like to do some seabed perspective by using the underwater intervention equipment. And finally, combine all of them to enable a digital blueprint. So this is a transparent ocean initiative in China. And in this context, so in lab, they already have launched some marine physical system to enable all of the surface one. So there's some gliders, some wave gliders, some underwater vehicles, some surface buoys, some cargo, and some onward glider, and so on. So try to put them together and to do some applications. So this is one case that by using two sea wing glider, and they can do the tracking and observation of the ocean vortex. And another case that's a last team in China also do some observation about typhoons. So by using a group of glider. And they also deploy some wave glider in the ocean, and this is the case. So all of them, by using all of this cyber physics system, so the lesson lab also presents some I4Ocean software to present the exceptional temperature data or conductive data or 3D ocean flows and about the speed and the vortex. So this is the context. So in this context, all of the research, in China on ocean science and technology, we would like to develop some new equipment. But of course, you know that we already have some history to build the autonomous underwater vehicles. So this is one case that the CR01 and CR02 could dive into around 6,000 meters. And this is another series of autonomous underwater vehicle. So my group also participates into a little bit about this vehicle. So from Zhihai 1 to Zhihai 6, so almost around 15 years. And you know that in another city in China, they also developed some other underwater vehicles, named as Qianlong 1, 2, and 3. So this is the case. And also for the autonomous surface vehicle, we would like to use it as a bathymetry for the oceans and also for the river. And we also would like to develop some surface vehicle from small size to big size. And this is a first autonomous ship test bed in south of China. So I will present some details later. So this is the context. This is the context according to the ocean science and technology in China. Okay. So according to my team and my research. Firstly, you know that I work in the Huazhong University of Science and Technology. We have the School of Navy Architecture and Ocean Engineering. So I lead the lab of advanced robotic marine system. So we have 2 research centers. So one is national level and one is province level. So we also have the towing tank since 1977, and we could do the test, hydrodynamic test, and some in-water test for our vehicle. So, and also in the school we have the Center of Underwater Systems. So we participate into some research activities about manned submersibles and underwater vehicles and remotely operated vehicles. So this some of them. So this was the manned submersibles, and this is autonomous underwater vehicles. And also we have some top-shaped vehicle, flat-shaped vehicle, and also we have towing ROV. So this is the history about center in the school. So as you know, I was one of the members of European projects Free Satellite. So when I came back since in 2011, I tried to build a lab of advanced robotic marine system. So mainly I focus on the guidance and control of marine robotic systems. So we have some surface vehicle, we build it, and we have some underwater vehicle. And also we use some weird robots in order to simulate the case of GPS denied for the underwater vehicle. And we also have some aerial robots. So we also have some collaboration with our previous partners and some new partners. So these are some prototype in our lab. So the first one is a flight type AUV, which will be used for the underwater cable tracking. And this is a top-shaped vehicle. And we also have some blue RV Sejong and hybrid Sejong and some mini AUV to train the students and to do the research. And we also have some sustainable surface vehicle. This is sailboat, and these are the surface vehicle. Small size, mid-size, and large size. And we also have some virtual floating operating system in order to simulate the underwater intervention. Okay, and this is the case that we have the AUV test in the towing tank. So this is a rough idea about the lab of advanced robotic systems. So what we have done in China, and especially I say that I focus on the guidance and control of marine robots. So first I will show you something about them. So the first case, that's if we would like to do the correlated seabed mapping or bus metering, we may need some fleet of them, either the surface vehicle or underwater vehicle. So in China, we try to build some surface vehicle, and we do the experiments. So we have 4 autonomous vehicles. We did the experiments in the lake near the university. So in this case, we try to build the formation. So it's the diamond formation to check the correlated control of multiple surface vehicle. So these are the real data feedback. So we connect it and draw it. So you see the vehicle could build the diamond formation, geometric formation like this. So, and these are the control performance for each of the vehicle, for 4 of them. Okay, so this is the formation keeping. And then we will try to change the formation around this time from the diamond formation to the straight line formation. So according to the according to the real data from each of the vehicles, so you can say that from here there is almost a jump for the control, because the vehicles have to change formation. So there is a change of the control commands. So you can clearly see it, and you can also see the path-following arrows for each of the vehicles. So the arrow is quite few, okay? And this is a straight line formation, but previously you see one vehicle is not so good because of all of the GPS are not aligned very well. So one of them have large offset over there. So this is formation switching from the diamond formation to straight line formation, and then go back to the diamond formation. So this is one of the case. And later, if we have the control method and algorithm, so we would like to go further by using the cloud-based smart cruise system. So this is a interface we develop. We can use it in the mobile phone, iPad, or even computer. So this is a 3D interface. We can deploy all of the vehicles, and these vehicles could be available through the 4G communication or by some other communication channels. So this is a real vehicle in the lake. So this is the idea that if we have some vehicles in this sea, in other rivers, or some other place, then we can correlate all of them through the cloud-based system. So this is the idea, and we developed this for the we developed this cloud-based smart cruise system for to implement the idea about remote scheduling, shipping and transportation, and some control and monitoring, and also some data connection. So this is the idea, and we also did some experiments about this cloud-based cruise. So it means anyone, anywhere, anytime can access the vehicles and to control the vehicles, or manage the vehicles, or schedule the vehicles. So this is the idea. So we have some surface vehicle or some ship. So if they can access to the cloud, then we can control it. And also we can have the history feedback through this interface. And we do the experiments to check the rough idea. And then we'll also try to be integrated to the European Marine Robotics Society. So we participated to the TN course. So just a few days ago, we did the experiments here. And yesterday, we used this kind of cloud-based cruise system to control 2 iPads. So in the swimming pool. So this is the result, and we will continue the experiments today to check 3 iPad vehicles. So this is one of them, and also just in this December we will test this system in the first autonomous ship testbed in China, in south of China. So this is the case. We will use this small size autonomous surface vehicle. And also we did some work about the sustainable and eco-friendly surface vehicle. This is a sailboat. So sailboats, I would like to say, if we would like to control the sailboat, it's a little bit much more difficult than the surface vehicle, because the sailboat have to interact with both the wind and fluids. So when we try to control the sailboat, we have to do the maneuver, zigzag maneuver or yo-yo maneuver. So this is a difficulty. And we developed the sailboat in the team, led by Dr. Xiaolong Yang, just in here, okay? And we do some experiments to check the sailboat, and this is a pre-planned path for them, and this is a real data feedback for the control of the sailboat. So you can see the sailboats move from start point and follow this kind of path by using the zigzag maneuver. And so just I think 1 month ago, we also attend the World Robotic Singing Competition. So this year, so last year I sent two students to Southampton to have a look what is sailboat, and this year we built a sailboat and we attended the competition. So it's very lucky that we sent 2 teams, and the 2 teams have a good place. I mean, it's the final competition. So one is the first place, and the second one is the fifth place. So this is the first time for us to send students to build the sailboat and to attend the competition. So I'm quite satisfied with the results. So this is the other side to show that we are a little bit good at control of marine robots. So this video shows some ideas to control 2 sailboats to build fleet, and also to do the station keeping, and also to do some collaborative area screen, and also to do some counterpart interaction during 2 sailboats. So this is the idea, okay? So this is a surface vehicle. We did some work about this one. And also we did some work about control of underwater vehicle. So for the underwater vehicle, we have one Sejong from Stanford University spin-off. So we did, originally this is a remotely operated vehicle. So we tried to turn it as an autonomous one. So we developed some control algorithm to control this overactivated vehicle, because in the horizontal plane we have 4 thrusters. So this is the case that we have to do the optimal control allocation, and also we try to do some saturated allocation by using some optimization algorithm. So this is theoretical part, and also we try to check it through the experiments. So before we check it, I show you this video about the robustness of the control of robot. So for the mobile robots or for the big dog, you know this from Boston Dynamics, is very famous. So through this video, it's quite intuitive that you know that the robustness for the robots is quite challenging and quite useful. So for the underwater robots, it's not so intuitive. So I compared with this video, okay? So in this case, we would like to control this underwater vehicle and send the command to set this vehicle to dive into around 1 meters, okay? So this is normal, this is not so difficult. But we try to make some disturbance, like the kickoff of the big dog or the small dog, okay? So right here, you will see that the vehicle is around 1 meters, but here, we will use a stick to make some disturbance, and then we will check the algorithm, robustness of the algorithm. So from here, you will see, so one student used the stick to push the vehicle, and the vehicle could recover around 1 meters. So this is one of the case to check the robustness of the control of marine robots. This is another case that we check it for the robust control of overactivated case. Previously, we used robust control for the depth, okay? But this one is for the horizontal plane. So, you know, for the horizontal plane, we have 4 thrusters. So in this case, it's much more difficult. So in this case, we have the continuous disturbance. So this is the orientation bar to show the orientation of the vehicle. So normally the vehicle have to stay around 0 degree, but we have the continuous disturbance and to disturb the vehicle, and then the vehicle have to recover to the 0 orientation. Okay. So there's something wrong with this video, I suppose, with this data. Okay. So this is the case that I also showed a little bit last year. So this year, 1 year more, we continue our work. So we can control the overactivated vehicle, either in the depth plane and also in the horizontal plane. So we also try to go forward, okay, to use this vehicle, to use this robot to do the automatic docking of marine robots. So for the autonomic docking, you know that for the docking, if the vehicle could dock into the docking station, they could be charged and have the data communication. So right now, many research do this kind of work. Okay, so in our group, we developed one docking station like this. So we have some lamp over there, and we have the vehicle. So in this case, we would like to command this vehicle to dock into this docking station. But what I would like to mention that normally for the docking, this is docking station, okay. So normally the vehicle uses this kind of algorithm to move like this way, okay. So this could be some problem because the vehicle could be stuck here. So in our case, I would like to use the path following algorithm. So you know that this is docking station. So through the visual feedback, we would like to build the arrows and build this central line. So what we would like to do for the docking is that we drive this vehicle to follow this path, and then the vehicle could be docked into this docking station without being stuck over there. So this is the case. So we have the experiments. So in this case, what we need is offsets between the vehicle and this center line, and also we have some orientation angles. By using this, we develop the we develop the modified path following algorithm. So we can say this is the case for the automatic docking. So this is a snapshot for automatic docking from 1 second to 46 seconds, and also we did more for the dynamic docking. Okay, so yesterday you also see some presentation about dynamic docking for the remotely operated vehicle. So we use this small size onboard vehicle to do the dynamic docking. So what we do is that, okay, we have one student to tell this docking station to move it, okay, but the vehicle have to dock into this station by using the visual serve feedback. So this is the case. This is the case. So this is real data, and this is depth. This is for the orientation of the vehicle. Okay. So this is a case that we developed in China for the control of marine robots. So this is one part for my presentation. So the third part is that the recent research institute. So this is the main idea for my presentation is the onboard fiber optical cable inspection. So because, as you know, that we have some historic experience to develop onboard vehicle and surface vehicle, and we also show some idea about control of the marine robots. So 3 years ago, we go to the competition, and we won the competition and get some major projects to develop a fly-style onboard vehicle to inspect the fiber optical cable. So what's the motivation? You know that there are around 263 subsea fiber optical cables, and the length, total length, is around 1 million kilometers by 2015. And also, you know that, for example, from China and to here, we have the communication. Okay, so most of the international network communication through outputs, around more than 95% of them are through the subsea fiber optical communications. So it's quite useful and quite important. And we also have many links between China and Japan, and we also have some other communication network. So this is the case for the global subsea fiber optical cable communication. But if we have the onboard cable, but there would be some problem because of the ship anchoring or fishing gear or dredging, or some to put some problem about the cables because of the hanging. So in this case, and because of uncovering, and also there's some natural disaster because of the earthquake and some turbulent currents to make the cable in danger. So we have to do the routine inspection and protection. So before I go to the aspects for the cable inspection, we would like to show you something about the layout and repair of the onboard cable. So this is the layout of the onboard cable, and this is the repair of the onboard cable. Okay, but you know, if we would like to repair the cable, we have to localize the cable and such that we could inspect the vehicle. So this is a challenge. This is a challenge. Of course, we could use some remotely operated vehicle, but this is depending on the company of the ship. So it's quite heavy cost. Okay. So, but of course, for the lever, they could only work for the shallow water, okay? For the ROV, so we say that it's high cost. If we have the autonomous surface, autonomous underwater vehicle could do this job to localize the cable and inspect the case of the cable, this would be nice. So this is the motivation why we would like to develop this kind of system. This is one challenge, okay? Another challenge is that okay, most of the fiber optic cable was buried because of avoiding the damage. So in this case, for the ordinary acoustic sensor, optic sensor, or laser, it can't work for them. So in this case, we would like to use the magnetic sensor to inspect or to localize the very thin telecommunication cable. So this is the magnetic sensor we developed in Wuhan. We have the collaboration with another university, so we have this sensor suit and we did some experiments. So with this idea that we try to develop this kind of flight style underwater vehicle mounted with two magnetic sensor to localize the underwater cable. So this is the underwater cable buried and very thin, so we have to use the magnetic way in order to allow us to inspect it. Okay, so for this, so we have the motivation, we know the challenge. So now we go to the implementation. So if there is a flight style vehicle and this is a cable, okay, so what we can do is that we also turn this problem into the path following style. So we could take it as a path, okay, but this path is not known in prior, so we have to localize it and to follow it at the same time. So this is a challenge. So we would like to use this magnetic sensor, two of them, to localize this cable and to know the offset and to know the orientation offsets between the vehicle and the cable. So we did some theoretical things and we published some papers, but the main contribution is that we developed the lower magnetic localization algorithm, and we also tried to address a little bit about the noise environment or noise case, and then we developed robust path tracking control. So for the magnetic localization, so we divided this case into three paths. So this is a this is a cable, buried cable. So it's vehicle. So if the cable is in the left side of the two magnetic sensors, and if the right or if the middle, we unify the localization algorithm. So this is the first time for us to develop this kind of algorithm. So this algorithm has been reviewed by the experts and published in IEEE Journal of Oceanic Engineering. And we also have some method to deal with the noise of the magnetic sensors, and we try to develop the robust controller to enable the buried underwater cable tracking. Okay, so this is one of the numeric results. So this is a cable. So this is a vehicle. So the vehicle could could localize the cable and follow this cable to do the routinely inspection. So this is the idea. Okay, and we also have the numeric simulation for the noise case and the time varying current on the sea. So this is the other case that we have the cable and we have the vehicle with with one pair of magnetic sensors. So this is the case. So this is a single, this is a controls performance, and this is the arrow. Okay. So this is the theory. Okay. So from theory we have to go to the practice. So we developed the localization algorithm by using a pair of magnetic sensors. So what we would like to do, next is to develop the real vehicle. Okay, so this is a vehicle we developed in China, and we designed it, and hopefully it will be done, and we'll do the lake test in next February. So I hope that we could have a chance in next BTS with our team members to share the information with you. So this is a vehicle we designed, and what we would like to share right now is that we work together with one company. Okay, so we developed this vehicle. I mean, from the mechanical parts and for all the controller or sensor deployment, and we collaborate with one company in China to do the modular design from both the mechanical and the functional point of view. So in this is why we would like to use this one, because we have this one. We have this magnetic sensor. So we put this as a module, okay? So without this module, this is ordinary fly-style AUV. With this magnetic sensor parts, so we can integrate it. So this is the idea. So this is why we like to develop this kind of vehicle with the modular design. So totally we have 1, 2, 3, 4, 5. So totally 5 modular. So the first part, so the second part for the magnetic sensors. So we have some cabin for the batteries, for the controller, for the other sensors, navigation sensor, and so on. Okay, so this is the case. So this is a modular design for the vehicle. So this is already on the way. Okay, so we will see it next February, and the deadline for our projects, I mean, for the test of the vehicle is next February. So I hope this would be done perfectly. And with this vehicle, okay, so with this vehicle, so we could, if we mount some magnetic sensors onto this vehicle, we could localize and inspect the onboard vehicle. So what we could do further is that we could to do some repair things. Okay, so for the industry class ROV, they could do this. Okay, they could do this. But what we would like to do is that we would like to use this vehicle and to mount 2 underwater manipulator. So this is dual arm, to do the dual arm intervention. So this is what we have done last year. So in this year, we did the experiment. So one team from China developed this vehicle, and this is another vehicle developed by my group. And we also developed 2 underwater manipulator. So this is the case, okay? And also you know that previously, for the underwater robotic community, normally we see 1 manipulator or 2 manipulators just mounted on the ROV. So this could be the first time for 2 arms mounted on the autonomous onboard vehicle. But you know that in US, there's a DARPA program and there is Angelo projects. They also would like to develop 2 manipulators. I suppose it is happening in 2018. So what we do for this one is in 2017. So we already developed 2 manipulators. So this is the case. So for in order to develop the dual arm and vehicle system, so firstly we have to design the motor. Okay, firstly we have to design the motor to get a compact design of the waterproof joint motor. So this is the case, and this is a final prototype for the waterproof motor. Okay, because of the time is limited, so I skip a little bit. So this is the case, and what we do for the underwater arm is that we also put the drive command board just attached to this motor. So it means, because this is the first time for us to do this research, so if there is some problem, we can easily open this cabin and to download our algorithm to do a little bit around the electronics board around here. So this is the case, and we develop it, and we also do the test to check this kind of underwater motor for the final prototype. So this is So this is a experiment, and then finally we assemble all of the joints. We have 5 joints, so we have 5 motors. We put them together, and this is a prototype, and we do the point-to-point calibration for the manipulator. So this was done, I think, last December. So just after the IEEE USYS conference, yeah. And also we do some dry tests for this kind of electric underwater manipulator. So there are 2 of them, so dual arm. So we do some dry test, and this is a video for the dry test. So this is the case that we have 2 arms, and we try to do the autonomous intervention to take this object. And also, what we would like to do is make a hack, something that's not only to precisely manipulate something, but also do some hack to get some objects. So this is another case. We also do the validation, do the experiments. And finally, we do the in-water test. So firstly we have the we develop a framework to mount 2 arms and do the in-water test. And this is the in-water test experiments, and these are the real data for each of this model. Okay, each of the model, either from the angle points, I mean the rotation angle, yeah, and also I suppose there's some force feedback. Okay, so this is the case for the in-water experiments for the dual arm intervention, underwater intervention. Okay, so finally we try to mount all of them to the underwater vehicle. But what I would like to mention here is the challenge between this kind of floating-based underwater manipulation. Because this one, this is ground-based, so there is always support. Even there's some difficult maneuvering for this kind of manipulation. But for this one, because it's in water, so we have to develop this whole system as a floating system. So if the manipulator moves, then the vehicle could be disturbed. So this is quite difficult for us. I mean, for the marine robotic community to do this kind of research. So what we would like to do is firstly to do the simulation, without disturbance and with disturbance. So this is the case that with disturbance. So here the base is fixed, but here the fix is moving. So through this kind of simulation, we would like to check the algorithm for them. Okay. And finally, we mount all of the mount both of the arms on the underwater vehicle. And we also have some vision feedback, but right now we didn't do it. We just integrate the 2 arms and the vehicle together, and we do the experiment. So next step, we will do the visual feedback to correlate all of the dual arm and the vehicle together. Okay. So this is a workspace for the vehicle mounted, for the arms mounted on the vehicle. So it means in this workspace, the vehicle could do the manipulation. Okay. And yeah. So we have the experiments in the towing tank. So this is an underwater vehicle, and these are the 2 arms. So in this way, we do the experiments in order to do the dual arm underwater intervention. But of course, I would like to say there's many lessons learned from this project. So if time is, because time is limited, we can talk a little bit if you are interested. And there are also a lot of open problems for this kind of research. So there are no way for us to do the dual arm underwater intervention. So that's all. Thanks for your attention.